Can you see my presentation?
Yes, sir.
In the last class, we have talked about some basic terminologies which are very relevant to machine learning approaches. Okay, so today we are going to see few more terminologies, and then we will be talking about the classification of learning problems, and we will present how we can design a machine learning system using several constraints and the uh, basic features. Okay, so in the last class we have talked about the domain, range, and data. Then we have talked about the supervised learning and unsupervised learning. Okay, so today we will see the classification of learning problems, and here you can see that there are four categories of learning problems, so which can be classified in terms of the range. Okay, so range may be finite range or continuous range, or if we classify the learning problems according to observed range and unobserved range, then similar to the finite range, we can have two different learning problems in each class. Okay, so if we divide the learning problems according to finite range and continuous range, then we can have the classification and clustering, which come under finite range, and we can have the regression and density estimation, which will come under continuous range. Okay, now if we consider the observed and unobserved range, then we can have two different classes. So observed range will include classification and regression. So these problems are basically supervised learning problems, and if we consider the unobserved range of data, then we can have the unsupervised learning problems. So unobserved range of data will include the classic learning problems like clustering and density estimation. Okay. Now here we can see that there are some problems which can be transformed from one learning problem to another learning problem. Okay, so here you can see that if we consider if we consider some classification problems in regression and neural networks, so we can have the logistic regression and neural some techniques in the neural networks. Okay, so those are basically the classification problem, but if we change the criteria in to some extent, then we can have the regression of those techniques. That means from classification to regression, we can transform those techniques after changing some criteria. Okay, so basically here the logistic regression and neural networks, these two different types of learning problems can be found common in classification and regression. However, the logistic regression is found to be a classification problem, but since it uses to predict some levels or some continuous value in the regression, therefore we can use this logistic regression for predicting some values. Okay, and similarly we can use the neural network techniques in both classification and regression. So we can classify the objects using neural network techniques, as well as we can predict the values or predict the labels in regressions. Okay, now if we consider the clustering techniques like model based clustering, then this model based clustering can be transformed into density estimation problem. Okay, so clustering is one type of learning problem, and density estimation is another type of learning problem. Now if we have some problems, if we have some learning problems in clustering, so those problems can be successfully transformed into density estimation problems. So similarly, we can have another type of modeling problem that is called the mixture modeling. So mixture modeling can be used both in clustering as well as in density estimation when unobserved range of data is provided. Okay. So here we can consider few more approaches like likelihood methods. So in the likelihood methods, we can transform the classification problems to density estimation problems like LDA, QDA, KDA, KDE in naive Bayes. Okay, so these are the different likelihood methods which we can transform from classification to density estimation. Okay. Now, there are some classification problems which can be transformed into clustering problems like nearest neighbor. And using classifiers, we can use. As I said in the last class, that clustering is a kind of classification in which uh, we use the unobserved range of data or unobserved data, so that can be classified into a number of clusters or number of groups. So clustering may be considered as a kind of classification. So using classification techniques, we can divide the unobserved range of data into some clusters or into some groups. So here classification, regression, clustering and density estimation. So these four are the dominant areas in machine learning problems. So based on these four dominant areas, we can have a whole lot of machine learning algorithms or machine learning techniques. Now, regarding these machine learning techniques, we can study two more important terminologies. Those are loss and risk. Okay. Now, what will be called loss? So, loss may be defined as the good approximation which is specified by some term specified by equation or function. So here the function is L. So L denotes the loss function. Okay, now L can be defined or L can be determined over the feature mapping. So this tilted x is, as I said, this tilted x represent the feature space, and this f over this tilted x means the function that we have defined over this feature space. Okay, now when it is multiplied with the approximated function f cap over the feature space, that means we are basically mapping this feature space into another feature space of high dimensionality. Okay, so this mapping is used to obtain the loss function. Okay, so loss function is determined or defined over this feature space, and we can map this feature space into r dimensional data or r dimensional space. So that is why we are using this notation, this arrow, to obtain this r dimensional feature space. That means from this feature space we map this feature space to r-dimensional feature space, and this r-dimensional feature space, basically what we obtain as loss function, that we get the approximate, okay, approximation of this higher dimensional feature space into lower dimensional feature space, or it may be the feature space which will have the dimension less than that of the earlier feature space. Okay, so now here xy, so for each x comma y, we can define this loss function. Okay, and this x comma y will belong to this feature space x into f of x. Okay, Now this loss function L of y comma this approximated function is the loss. Now how can we relate this loss function to some machine learning problems or learning problem? So if I consider an object recognition task or object recognition problem, then we need to find the class levels of some unknown objects. Okay. Now in that case, how when we determine the class level for some unknown objects, that means how close that objects is found to be the actual object. Okay, so with actual objects we train the model and we build up a trained model, and with that trained model we will now going to classify the unknown objects, and after classification we will assign some levels to the unknown objects. Okay, now this loss function is used to find the good approximation. So good approximation means how close the unknown object is found to be close to some actual object, or how far the unknown object is found from the actual object. Okay, so this is the approximation over this feature space, and this approximation is represented by this r dimensional feature space. Okay, this is another feature space. This is the feature space on which we define this loss function. Okay, so for each x comma y that belongs to x into f of x, this L of y comma approximated function fx is the loss or penalty. We can also use the term penalty in place of loss. Now this loss function is with this function. Okay, f cap of x. So this is the approximated function, and this can be associated with this y. Okay, now we can have some loss functions which may be the squared error loss, absolute error loss, zero one loss, or a cross entropy loss. Now, the first two loss functions can be used in regression models. So, if we consider y is the actual value and f cap x is the predicted value, then we will find the deviation between actual value and the predicted value. Okay, and we will take the square of that deviation. So this will be defined as the squared error loss. Okay, now if we consider the absolute error loss, so we will take the absolute value of deviation between the actual value and the predicted value. So this is the approximated value. Approximated value means this is the predicted value. Okay, now if we subtract the predicted value from the actual value, then we take the then we take the absolute of this deviation, then we get the absolute error loss. Okay, so first two loss functions or penalty functions can be used in regression models. Now if we talk about a simplified classification, simplified loss function for classification problems, then we could have a 0 1 loss. So in this 0 1 loss, so we would have a matrix, C by C matrix. In that square matrix, all the diagonal elements will be found to be 0, and the positive values will be found off diagonal. That means the off diagonal values will be found to be positive or 1, and all the diagonal values will be found to be 0 in that square matrix C by C. Okay, now according to that loss matrix, so we can define the 0 1 loss. So what is the 0 1 loss? So 0 1 loss can be defined as defined as L of y comma, this is the predicted value. Okay, so actual value comma predicted value, this will be assigned by either 0 or 1. So when it will be assigned by 0, when the predicted value is found to be the actual value, okay, and when the predicted value is not found to be equal to the actual value, then we will assign 1. So first we will assign 0 when the predicted value is found to be equal to the actual value, and we will assign 1 when the predicted value is not found to be equal to the actual value. So this is called the 0-1 loss. So this is most simplified form of loss function which is used in classification problems. Okay. So next we can talk about the cross entropy loss. So this cross entropy loss in most of the cases we use in classification, but when we invoke or when we use the joint probability distribution along with the conditional probability distribution and marginal probability, then we can transform these classification problems into regression problems. And in that case, when we transform the classification problems into regression problems, then we could use this cross entropy loss function. Okay. Now this cross entropy loss function is defined is defined to predict the class levels or some unique information provided the features value for all the classes. So if we consider there are c number of classes or c number of different types of objects, okay, then for all c number of classes, we will estimate the conditional probability for class level y, and then it becomes the function of cross entropy loss. Okay, that means this cross entropy loss function is defined uh, over the conditional probability that is used to find the class levels given class levels when the features of all the classes are provided or given. Okay, so in another way we can find this, or we can define this cross entropy loss function. So in place of in place of this equation, we can write this form minus log of approximate. This is the approximated function. That is in place of this probability we can write f cap fx. Okay, so this class level, so here capital Y is the class levels of all c number of classes, and this becomes a specific class level. Small y becomes the specific class level. So when this will be determined, when the feature vector x will be given. That means this capital X represent all the feature vectors. Okay, that means all the feature vectors will contain in this x, capital X, and this small x represent any feature vector. Okay, any feature vector of C class. So we can represent this cross entropy loss in this way also, in this form also. So this is nothing but the entropy equation. So we can use this entropy equation to define the cross entropy loss function. Now what is risk? Or we can, in other way, we can say the generalization error. So if there is some criterion for good approximation f cap of function f, then this good approximation or just approximation can be used to minimize the expected loss. Okay, now if this approximation f cap is found from or found on the function f, then this approximation can be used to minimize the expected loss. So first we determine the loss function, then then we are going to minimize that expected loss, which is known as the generalization error or risk. So before we determine the risk function, we need to determine the loss function. So once the loss function is determined or defined, then we will try to minimize that expected loss, and this will be called the generalization error or risk. Now, usually we can use the expectation with respect to the joint probability distribution. Okay, so these are the random variables x and y. So x may be considered as the feature vector, and y may be considered as the class level. And combination of these two random variables may belong to this feature space. Okay, belong to this feature space. Okay, now we can use this expectation to obtain the generalization error or risk with respect to the joint probability distribution. Okay. Now the risk of approximation f cap at point x that belongs to this feature space tilted x, so is the expected loss incurred by using this f cap of x. Okay. So in place of y, we can write this approximated function. Okay, so if we consider there is some point x that belongs to this feature space, then we can define the risk of approximation f cap. Okay, so which would be the expected loss incurred by using this approximated function in place of y for this data. So for this data means this random variables x and y. Okay, so such that x equals to x. So as I said that this capital X represent all the features vectors. That means with that set of features vectors, we can obtain some feature vectors small x. Okay, so from that set of feature vectors, if we choose a specific feature vector, then we can define this risk of approximation function f cap. Okay, so here we can define the risk of approximation r of this approximated function given x equals to x. So this is nothing but the conditional probability distribution. So we can represent this risk function or the generalization error in terms of the conditional probability distribution. So R of f cap given x equals to x. So this will be written in terms of the expectation. So what would be the expectation? So this expectation would be defined with respect to the joint probability distribution. Okay, so in terms of the joint probability distribution, so here we can have this joint probability distribution. So in place of f cap given x equals to x, we can write this form. So this is the another form of generalization error or risk by which we can minimize the expected loss. Okay, so either we can write this form. So this is very simplified form, or we can write in terms of expectation. Okay, so this expectation, when we find the risk in terms of the expectation, then we will have the risk of approximation in terms of expectation that will with respect to this joint probability distribution. So joint probability distribution means this joint probability distribution will be defined over the random variables x and y, where x represent the feature vectors and y represent the class level. Okay, so this is another form. So integration over L of actual value, this is the predicted value, and that will be multiplied by the probability. This is the conditional probability. So this will be multiplied by the conditional probability of y given x. Okay, and in the range fx. So this is the range. So range of this integration would be fx. Okay, so this fx is the, as you know that x is the feature space and fx is the undefined some unknown function which is defined over this feature space. So this would be the range of this integration, and this integration will be defined over this loss function. This is nothing but the loss function, okay, and that will be multiplied by this conditional probability distribution. So p of this is the probability of y given x. Now here the capital Y, here you can see this capital Y represent a set of class levels. So we can use this capital Y as a response variable, okay, and if we consider this response variable is found to be some random variable with the conditional distribution p of y given x, okay, when the input x equals to x and trend classifier f cap are treated as fixed, okay, that means this input x equals to x and the trend classifier, this approximated function f would be found as known. That means this would be fixed value, okay. So for input x and the approximated function, because this approximated function that we obtain in the obtain in the computation when we determine the loss function or penalty function, and this would be the fixed value. So this input feature and this approximated function, then we can obtain this conditional distribution p of y given x. Now if we consider a feature space, and over that feature space if we define some unknown function, okay, so unknown function means this function is not known to us. Or if we consider the joint probability distribution p of x comma y, that means this joint probability is defined over the random variables x and y. So the questions come whether these functions actually exist or not. If these functions are exist, then it will be easy for us to build up a mathematical model, and mathematical model using some learning technique. But if if these functions do not exist, then it will be difficult for us to obtain some mathematical model over this feature space, okay. Now what do we do if we have some imperfect state of knowledge? Then imperfect state of knowledge can be uh, uh, can be expressed by some probability distribution, okay. So probability distribution, we can use the joint probability distribution, we can use marginal probability, we can use conditional probability distribution, okay. So this will be the this would be the case when we have the imperfect state of knowledge, okay. So if we have some unobserved data, so data is not known to us, but if we have some feature space, and in that feature space if we have some unobserved data means the data are not labeled data, okay. If we are not using the labeled data, then for clustering and density estimation, so we can use this joint probability distribution, we can use marginal probability, and we can use the conditional probability distributions to obtain some model which relevant to the learning problem, okay. So learning problem that we are going to that we are interested to solve, like clustering problem and density estimation problem. So in that case we can obtain some mathematical model from unobserved data, okay, using this probability distribution functions. But if the data is known to us, that means if we use the label data, then that will be called the observed data. And from observed data, it is very easy to define the function f and other probability distribution functions. If we use the so in that case we do not interested to have this joint probability distribution function. We can use some simple model to obtain obtain the train model for classification and regression. But in case of clustering and density estimation, when we have the unobserved data, in that case we can use these probability distribution functions. Now the questions come, how to select the models. Okay, so if we have the training, how to select the training, uh, how to select the training models, and if we have some computable optimal criterion, okay, like the training risk, if we define or if we determine the training risk on some observed data or unobserved data, then for this optimal criterion we can have some approximations. Okay, so these approximations, this approximation will be known as the optimal approximations. That means this optimal approximation can be determined only when we have some optimal criterion. Okay, so optimal criterion like training risk. So what would be the training risk or what would be the penalty? So if those criteria or those criteria are known to us before we obtain the optimal approximation f cap, then it will be easy for us to obtain this type of approximation in the set of all functions. So in the set of all functions mean, so this tilted x represent the feature space. Over this feature space we obtain all such functions f of x. Okay, now we will determine this optimal approximation f cap in the set of all functions when this optimal criterion is given to us. When this optimal criterion will be provided to us, like the training risk or loss, or the what would be the loss, what would be the risk, if these values are provided to us before we obtain the optimal approximation in the set of all functions, then it becomes easy for us to obtain such approximation in the given feature space. Okay. Now the purpose of each regression and classification method is to specify a subset P of the set of functions mapping function mappings from x to fx. Okay, that means if we are able to specify a subset P, okay, for classification or regression. So here P would be considered as P may be very small or small enough that from where we can obtain the optimal approximation. Okay, or it may be very large. That means this subset may be very small or it may be very large. Okay, now so two different cases we can have. So this P, so this P belongs to this P belongs to this feature space. Okay, now if this optimal approximation we are able to determine which belongs to this subset P, then this can be found on this small subset. Small subset means when the P is found to be small subset. When P is found to be big enough or close to the feature space, then we can have these assumptions which will be called the model of assumption, or we can say simply we can say this is model assumption. Okay, now either we can use the small subset, or we can use the big subset. So this both this big small subset and this big subset belongs to this feature space of all the functions. Okay, this fx. Okay, so here and the optimal approximation that we obtain when the optimal criterion is provided, so that will belong to this subset P. Okay, and this P is known as model assumption. What we call this P? P is known as model assumption. Okay, and the computation of this FS. So this is the FS. So from a data set is called the training model. Now if we consider a data set S, okay, and if the model assumption is determined over this data set S, then this approximation also belong to this subset P. Okay, so this is called the training a model. So when we train a model for classification or regression, so we need to have such type of model assumption. Okay, and over this model assumption we will define this optimal approximation from a dataset S. That means this dataset will be provided to us, this optimal criterion will be provided to us, and if both this information are available, then only we can able to design a trained model, okay, from this model assumption. Now sometimes P can be described by finite number of scalar parameters. So in that case we can call that method parametric method. Okay, parametric method means these scalar parameters are found to be finite. Okay, so we can use a finite set of scalar parameters. So when we have the finite set of scalar parameters for this model assumption P, then we call that method parametric method. Otherwise we will call that method non-parametric method. Okay, non-parametric method means that uh, we have large number of parameters, large number of parameters, so which is not defined for this model assumption P. Okay, so this is called the non-parametric method. So in that case the method will be called non-parametric method. Now there are two types of learning problems that we can have. One is the predictive learning or predictive modeling. Another is the explanatory learning. Now what will be called predictive learning? Now the first, if we want to, if we have the unmarked features, vector like xn plus 1, okay, xn plus 2, and so on. So if we have been provided these unmarked feature vectors, then we can make some assumptions or we can make some prediction of over this unobserved data, and this unobserved uh, these predictions will have some responses for if we consider the problem is the regression problem, and these unobserved predictions have some class levels. Okay, so for classification, so if we consider the classification, then on this unobserved data we can predict the class level. If we consider the regression models or regression problems, then on this unobserved data we can have the predictions which will which would be the responses. So we can have the responses and class levels over this unobserved data. Okay, and which will be specified by this approximated function f cap of xn plus 1, f cap of xn plus 2, and so on. So these approximated functions are determined on these unmarked feature vectors as responses or class levels. Okay, when the class levels are provided, then the class levels for on class levels for unknown data would be predicted, or class level when the class levels are not provided, then we can have the responses for regression problems, okay, or regression models. So this type of problems are called the predictive learning or predictive modeling. Now the second type of problem we can have, so that find the relations between observed features vector and their corresponding observed response or class levels. Okay, so if we consider the feature vectors are x1, x2, and xn, so these are the feature vectors, and the corresponding observed response and class levels are y1 to yn, then we can find relations between these two information. Okay, these two information about the feature vectors and information about the response or class level. So solving this type of learning problems is known as the explanatory learning or explanatory modeling. Okay, so
Sir,
we can have two different types of modeling problems. One is the predictive modeling, another is the explanatory modeling. Any
sir,
questions?
yes, sir.
Hmm.
Sir, when we are finding the prediction on basis of the self-predictive modeling, so then also I think that for finding the prediction of x n plus 1, the f cap x plus 1, we need to find the relationship between x1 y1 and x2 y2 xn yn, which are
No,
known.
no.
Is it?
As I said in the previous slide, that when we have unobserved data. Okay, so unobserved data means either we can perform the clustering or density estimation. If we go for clustering problem, then obviously we need to apply some classification strategy so that we can divide the unobserved data into a number of clusters or number of groups. Okay, so in that case, the class levels or response are not available. So what we call this type of learning problems, for this type of learning problems, so what would be the best possible way to represent? So what would be the best possible way to represent this learning problem? So best possible way to represent these learning problems might be the predictive modeling, might be
Okay,
predictive
sir.
modeling. Okay, so in the predictive modeling, we try to find the clusters. Either we try to find the clusters, or we determine the density of the density over some feature space. Okay, so which will be called the density estimation. So this predictive modeling strategy can be used when we have the unobserved data. That means on the unobserved data, what we are trying to find, we are trying to determine the unobserved response and class levels. So these are not known. Unobserved response means these responses are not known to us. Unobserved class level means these class levels are not known to us. So when this type of unobserved responses and unobserved class levels are found, when we deal with clustering problems or density estimation problems. So in case of the clustering problems, so basically, these clustering problems try to find some clusters with some meaningful characteristics. So when we determine the uh, cluster, then that cluster means we can say that, or we can label that cluster as unobserved class level.
Okay, sir.
Okay. So that is why I am using this term unobserved responses and unobserved class levels. But in this case of explanatory learning, we are having both this information, feature vectors as well as the class levels or response. So both these informations are available to us. Now we will be trying to find the relationship between these two information. Okay. So this is the simple task in which we try to find the relationship. So in case of classification or regression, we can use this strategy. So this is nothing but the explanatory learning in which we try to find the levels of some unknown objects or unknown images, or we try to find the regression values, or we try to find some predicted values in terms of the given these two information. Okay. Now, how we can design a learning system? So there are some attributes of the learning system, like choosing the training experience. So we have to choose the training experience. We have to choose the target function. We have to choose the representation of the target function, and we have to choose the function approximation algorithm. So these four are the attributes of a learning system. Okay, so when we design a learning system, so we need to take care of these attributes so that we can carefully we can carefully choose these attributes for the learning system that we want to build. Okay, now what are the different information that we can use in choosing the training experience? Okay, so one key information or one key attribute can be whether the training experience provides direct or indirect feedback regarding the choices made by the performance system. Now, so regarding this information, if I consider a checkers playing game, in the checkers playing game, so how does checkers playing system learn about the moves? Can you tell me? If we consider the checkers learning problem or checkers playing game, so how the checkers playing game or checkers learning system learn about the moves?
So by playing with itself.
Playing with itself or playing with some
Human.
human opponent. Okay, if the opponent is human, then either by learning from uh, uh, learning from winning the game or lost the game. So when we have a set of board state, or we can say after every move we can have a new board state. Okay, so if we quantify that board state, or if we quantify every move, then we can have we can have a large search space. Okay, so from that search space we can use the learning experience, or we can use the such training experience for learning of the learning of the system. Okay, now this is the one aspect, and another aspect is that if we have the other information, like the sequence of moves and the result of the game. Okay, so these are the another type of information that we can have. So one information is we have a set of board state. Okay, so this set of board states is obtained after every move. Okay, so if we have a number of moves, for that number of moves we have a set of board states, then we can either feed this info first type of information, or if we have the sequence of moves along with the game result, then we can also feed the second type of information to the system for learning purpose. Okay, so in the first, if we use the first information, like the set of board state, so in that case, the training experience will use the direct feedback information. Okay, and if we use the second type of information, like the sequence of moves and the game result, then this becomes the indirect feedback. Okay, so either we can use the direct feedback or indirect feedback for uh, uh, for training. Okay, for training the model or training the system. Now, the second important attribute of the training experience is the degree to which the learner controls the sequence of training examples. Now, how this can be achieved? when learner controls the sequence of training examples, so in presence of some supervisor or in presence of some teacher, what we call in the supervised learning, that when the supervised learning is performed in presence of teacher or in presence of supervisor, then only we can control the sequence of training examples. Okay, that means once we decide the number of board states that will be used learning by the learning system or the train model, then we can control the sequence of training examples. So here the training examples is one training example means the board state. So after each move, there there will be a board state. So we can have a number of board states. Okay, number of board states for number of moves. Now if we want to control the sequence of training examples or sequence of board states, then there would have some uh, supervisor like entity. Okay, this supervisor like entity will be integrated with the training system or the learning system, and that will control that will instruct the learner to control the sequence of training examples. Okay, so that kind of entity will help to control the sequence of training examples. Now the third important attribute of the training experience is how well it represents the distribution of examples over which the final system performance P must be measured. So if we consider the well representation of examples, well representation of examples means either we can take a small number of training examples, or we can take large number of training examples. Now what would be chosen by the learning system? Either we can select the small number of training examples, we can select large number of training examples. Now in this situation, it is very difficult to find the optimal number of training examples. So best possible way to obtain the optimal training examples is to uh, obtain the approximation of the approximations over number of training examples. Then we can decide whether the training examples are found to be well distributed or not. Okay, if that many as training examples give the good performance, then obviously we will say that the distribution of training examples are good. Okay, otherwise we will go for the other distribution. So in this way we can have lots of distributions of training examples. So among those distributions we have to select the most uh, the well represented or well distributed training examples, so that we can find the optimal performance for the learning system. Okay, so these three vital informations is used for choosing the training experience in the learning system. So in order to complete the design of the learning system, so we can choose the exact type of knowledge which is to be learned. Okay, a representation for this target knowledge and a learning mechanism. So these three can be selected for the learning system. If you have any questions, you can ask me. Otherwise, we will stop now, and we will continue the same topic in the next class.
So slides.
Yeah. Today I will send you all first three slides. Okay, to your mail ID.
Okay, sir.
Okay, that's all for today.